say, oh, it's easier to be online. That's true. But the real problem is that compared to before, you assume people need it because it's
Yeah.
Yep. Yep. All day, every day. Yep. And so by the time Colloquium's up as
I get it. Hey there, I'm Gary. Oh, I was just about to ask if you'd log in so we could. We're sharing.
So you can either sit in the front row, you can stand up here to the side for a minute.
Oh, okay, because you got an intro, right?
Yeah,
okay.
Oh, right there.
Yeah, if you don't mind, I'll just leave that there.
Okay. Good afternoon, everybody. I'd like to get started. If we could. Hello, everybody here. Hello, everybody online. Thanks for joining us today. If you don't know me, my name is Bill Blair. I'm a research professor at Hopkins. And it's my pleasure today to be able to introduce our speaker, Danny Milisavljevic from Purdue University. Danny got his undergrad at McMaster University in Canada and did a master's thesis on the philosophy of and history of science, which I think is pretty cool. Then he went to Dartmouth and got his PhD with Rob Feason at Dartmouth College in 2011. From there, he was a postdoc at the Center for Astrophysics, spending 6 years there, 3 years with the Smithsonian side and 3 years with the Harvard side of the house, working with Alicia Soderberg on transients and then with Dan Patnod on young supernova remnants. Since 2017, Dan has been at Purdue in the Physics and Astronomy Department, and he's an associate professor there since 2023. Dan has worked on many areas related to supernova remnants and supernovae. I think he's best known maybe for working at that intersection between the old supernovae and the young supernova remnants and trying to, in particular, I think we'll hear some today about using young supernova remnants to try to diagnose the precursor star, either explosion mechanisms or the kind of star it was and that sort of thing. But related to that are all kinds of things like stellar feedback and massive stars and nucleosynthesis, the formation and destruction of dust, and of course the transients in a more general sense than just supernovae. And he's worked in all those fields at some level, but today we're pleased to have him here, and he's going to tell us about supernova remnants, laboratories for extreme physics and cosmic calibration. Danny, welcome. Thank you.
Great. Thank you very much for that kind introduction, Bill, and thank you everyone for the invitation to speak here. I really am humbled. This is the place where the magic happens with Things Space Telescope, and I've just been delighted with the opportunity to meet with people, discuss ideas, and I look forward to that moving into tomorrow as well. I come here alone, but I'll be presenting the work that represents the efforts of many people, and I want to acknowledge them. That starts with my own research group at Purdue. I think the slide summarizes what it's like to have me as a supervisor. And then also the legion of supernova superheroes that I get to work with around the world, including a variety of alumni and faculty at Purdue that aren't in my immediate research group. Bill already touched on what I'm going to try to address today, which is basically providing an overview of the importance of supernova explosions and then addressing some of the key outstanding questions regarding their progenitor stars, so the types of stars that are exploding, and the physics of the explosion. My talk has an emphasis on core collapse explosions, which I think is complementary because I know that Carlos Badenes gave a colloquium a couple weeks ago on type 1A explosions. So you get back-to-back, stem-to-stern touch on supernova explosions. I'll briefly discuss my own research with 3D reconstruction of supernova remnants and trying to use these debris fields to understand these key outstanding questions that I brought up. And then how can I not spend substantial time highlighting all of the new possibilities for addressing these questions now that we have the James Webb Space Telescope. I thought it appropriate, given the timing, that I acknowledge that we just passed the 39th anniversary of the discovery of supernova 1987A. So there's the progenitor star, Sanduliak -69202. And there's the explosion co-discovered by Ian Shelton and Oscar de Halde. And of course, an abundance of rich information that's been made possible by this very nearby event and our subsequent monitoring by facilities such as Hubble Space Telescope. So here's an enlargement. I could spend the whole lecture and more discussing everything that you see there. I love how I can walk up to the screen, though that doesn't help those at home. This ring and this ring are not the explosive debris that was released by the star system prior to explosion. We think that the inner ring was ejected about 20,000 years by a merger of two stars. Okay? But it's the stuff inside, that's the ejected material. And over time, we've been able to watch as the supernova blast wave interacts with that surrounding wall of circumstellar material. You see here the first hot pocket lit up and then more lit up with time. And then the expansion of the stellar debris. And notice it looks spherical, but with time, as the opacity goes down and we have preference in expansion, we see that it's actually not a spherical expansion, but it has some almost bipolar morphology to it. Okay? So many things here that standard theory didn't immediately predict beforehand. It was only having the power of resolution in a nearby object by being able to address that. Okay? And also a reminder that 87A was the first multi-messenger event. I know a lot of attention gets to the neutron star merger, but it was 87A for which we detected the first neutrinos outside our own solar system. And with present facilities, we will potentially detect thousands of neutrinos from the next galactic supernova. Perhaps I can come back another time and tell you about the supernova early warning system, which is a network of neutrino experiments that's going to let us know when that happens. So why is this important? We're in an audience of experts, of course, but here's a laundry list of all the different ways that supernovae impact astrophysics. So if we're talking about galaxy evolution, of course, they introduce a tremendous amount of the energy balance, structure, and chemical makeup. From star death, we can trigger star formation. They're a significant source of dust, which is a contributor to new stars and planets. They produce a variety of exotic objects for which we can study extreme physics around neutron stars and black holes. I just said they produce neutrinos in prodigious amounts. They're also the progenitors of the gravitational wave system. So the neutron star mergers, the black hole mergers, those all came from individual supernovae. And the supernovae themselves are gravitational wave producers. And of course, we're all glad to be here today due to supernovae providing an abundance of the heavy elements. So of the many questions one can ask about supernova explosions, I have two that I will highlight and return to throughout this talk. One is, what are the types of stars that explode? In that first example, supernova 1987A, okay, that was a blue supergiant, which contradicted the common interpretation that the natural progenitor star for a hydrogen-rich explosion would be a red supergiant. Okay? Now, theorists very cleverly retroactively predicted that a blue supergiant could explode, but it was, a first confrontation that, hey, we don't have the whole story straight. Since that time, we actually see yellow supergiants exploding in a variety, so we don't have that whole story complete yet. Next is, how do stars explode? Yeah, I'm going to go through the kind of cartoon Astro 101 explanation of collapse and explosion, but there's a lot of important details that we don't have finalized. And I'll tell you something, I'm coming across a 20-year anniversary for myself of how long I've been studying this thing. And when I started, I thought I could study how stars explode just by themselves without understanding what types of stars explode. I thought it was more stamp collecting, the types of stars, the progenitor systems. But in fact, the more that we've investigated, we find that how an explosion proceeds is actually largely driven, hugely influenced by the type of star and its progenitor structure leading into core collapse. Okay? So in fact, I cannot understand how stars explode without understanding the progenitor star and its interior structure in the phases leading up to core collapse. So let's just walk through this very briefly. Massive star goes through successive stages of hydrogen fusion, of fusion, starting with hydrogen at the core. This builds up this onion skin interior until it reaches iron. Iron fusion is no longer exothermic, it's endothermic. It robs the core of that radiative pressure. A collapse begins. Electron degeneracy pressure saves us for a little bit, but not for long. There's a collapse. We have electron capture onto protons producing neutrons. We have photodisintegration. That leads to a point at which the neutrons get too close together and the strong force kicks in. There's a little bit of a rebounding shock as things stabilize. And that prompt shock was thought to disrupt the star, causing the supernova. However, decades of simulations weren't able to reproduce that thought process. The system, the star, would just continue to collapse. Now, we know we have black hole systems, okay? But we also know we have successful explosions. So something in the ingredients wasn't quite right. And we think that neutrinos are a key driver of most supernova explosions. There are other ways, largely related to rotation and the development of magnetic fields. But whatever you want to introduce as an additional driver beyond that prompt shock, it appears to be that asymmetry is a key ingredient for successful core collapse explosions. Okay. Going back to what I said earlier, there are a variety of theoretical and observational work showing that the interior structure of the progenitor star immediately prior to the explosion may be very turbulent and mixed. So this Wikipedia stellar interior onion skin that I've shown you is a bad thing to have in mind. So certainly fine as you go through most main sequence, but as you approach core collapse, try to envision something much more dynamic. Okay? People are talking a lot now about shell mergers approaching core collapse. Okay, we have fusion processes, density gradients, lots of entropy happening, and there may be instabilities. Okay, the extent to which, how prevalent they are, that's all work in progress. Okay? One of the reasons we think this is that observationally, and this is now taking an example from an extragalactic supernova, is that stars happen to be doing things, many star systems are doing things preluding core collapse. Okay? When I was in grad school, now where are the students? I met with the students today. Maybe there we go. When I was a student sitting there, I was told you'll never be able to predict when a supernova explosion is going to happen because the core activity is so far removed from the envelope. Okay? And yet, here's a system, this is timeline, this is explosion, depending on who you talk to, that's the explosion or that's the explosion, but let's just say the supernova happened here and it was terminal. Okay? But preluding that, there was this precursor activity. And you see here, it's called Supernova 2009 IP, which is a dumb name because the actual explosion took place in 2012. But there was a supernova imposter. There was an outburst with energy insufficient for a supernova explosion, and then it dropped down. Then there was additional fluctuations leading up to this terminal explosion. We interpret this as the star ejecting massive amounts of material as it leads up to core collapse. Okay? So we take the hypothesis that this close timing between the end of the star and this mass loss are related. And that means information from the core is leaking out to the envelope. Okay? So hence, again, why we think that interior structure is perturbed. And to drive it home even further, whether or not a star successfully explodes, as demonstrated in simulations, can be determined on the level of perturbations in the interior structure, which is to say, if you had a spherically symmetric interior, unsuccessful explosion. If you perturb it in a certain way, a successful explosion. So that's why there's become this great importance in understanding the progenitor star and its structure leading up to core collapse. Okay. So how are we going to study this? Okay. Very popular way, and many friends in this room do this, is using extragalactic surveys. Okay. You have strength in numbers, which is great, but okay, there's an unavoidable challenge in interpreting an unresolved dot in the sky. Okay. Now, not to throw shade on people who study dots, but if you want to understand 3D information from a dot, it's challenging. We're very clever as astronomers. We can do photometry, spectroscopy, polarimetry. We can look at it from various wavelengths. But to get 3D information from a dot is hard. Okay? And even moving into the era of Rubin Observatory, where we may find upwards of 1 million supernovae per year, which is outstanding. I made this plot for my class. If you sum up all the supernovae discovered until now, it's around 100,000. Okay? In the first year of operation of LSST, it's going to be over that potentially by an order of magnitude. Okay? But even then, what are the nature of the events? Okay, so here's the template image, here's the science, this is the difference. That's your object. Sometimes supernova people like to show the science image to show, look at the beautiful galaxy in the supernova. No, you're only studying that thing, the dot. Okay? And you're trying to understand 3D information from a dot. Okay? Now let's switch to remnants. I can roll up my sleeves. Now I can see things. Okay? I can get both kinematic and chemical information that's spatially distributed. Okay? Can understand where elements were ejected with certain directions. Okay? But of course, I have to admit that remnants are not perfect. They have their own set of limitations. Okay? One limited number. There are only hundreds of remnants that are known in our Milky Way galaxy that are of sufficient nearby distance to be able to do this kind of analysis. And then also the question of nature versus nurture. When I look at G292 and 132D, I have to be very careful to disambiguate what's intrinsic to the explosion. So when I look at that morphology, was it due to the explosion dynamics, or was it a result of interaction with the environment? Okay. So that's why for a lot of the science that I try to do, I prioritize the youngest remnants that have had the least amount of interaction with the environment. But even then, okay, we always have to be aware of that complication. Cassiopeia A is the remnant that I'll be focusing on in this presentation. There's a variety of reasons why you would select it. It's the youngest example of a core collapse explosion. We don't have an exact age because there's no credible historical sighting, but we can watch the movement of the filaments and actually trace back to that explosion date pretty well. It has a spectroscopic classification, which is amazing. Nobody saw it when it exploded. How do we know what the spectral type is? Well, through light echo spectroscopy. And actually that's been done from multiple lines of sight, where we've seen direct evidence of asymmetry because velocity differences depending on which line of sight you use. There's a variety of other reasons why it's the good one to go after. And then I like to just put here at the bottom another reminder of the motivation for doing studies of these remnants is, supernovae have their importance in the growth and development of galaxies, and many people in this building try to understand our cosmic history, okay? And if we're going to have any chance of interpreting data from the distant universe, we need robust measurements made from resolved phenomena in our own backyard, okay? That's things like energy, kinetic energy, the nucleosynthesis yields, the distribution, the dust output and destruction, okay? These are the kinds of things that supernova remnants can provide. Because I'm talking about Cas A so much, let's just do an anatomy, a very brief course. This is a multi-wavelength image. We can start with the outer edge. This is the forward shock. So that's that prompt shock that started near the core, ripped through the star, okay? It's propagated outward. Now what's wild with Cas A is there's actually material out ahead of the forward shock. How can that be? Because this was the fastest stuff. Well, over time, as it snow plows through surrounding material, that forward shock slows down. And then this stuff, which was originally slower, isn't as slowed down because as a smaller cross-section, it actually catch up and race out ahead of the forward shock. In the center, that's the surviving neutron star that formed. This bright stuff, what we call the main shell, that's the bulk of the explosive debris, traveling at about 5,000 kilometers per second. And then in the northeast and southwest, that's a whole other presentation. I mentioned these outflows of high-velocity ejectonauts that are sulfur silicon enriched. This is what it looks like in 3D. I like to show this because people see 2D images all the time. It's not as often that we get to see an astronomical phenomena in 3D. This was made through a variety of radial velocity measurements in the sulfur and oxygen lines in the optical. What I want you to take away from this is that it's not random. There is large-scale coherent structure that the explosion dynamics imprinted on the ejecta. Okay? And on the side here, I show a Mercator projection. I made this because I'll never forget the first time I had a presentation, a radio astronomer said, "Oh, that your eyes are leading you to find structure where there is none." Well, look at this. We have a Mercator projection. We have continents of ejecta. There is a clear ring here and then smaller rings as well. Okay? Now, the origin of those rings, okay, we think it's largely driven by these nickel-rich plumes that were moved outward by uneven neutrino heating early in the explosion. So in red, we have optical, which is sulfur and oxygen. X-ray, we're showing the iron. Now, the iron is a decay product of cobalt-56, which was a decay product of the nickel-56 produced early in the explosion. This is a simulation, seconds after explosion and hours after explosion. You see the nickel racing out ahead of the lighter elements. Those race out, and as they decay, they provide a pressure on the lighter elements, carving out cavities. Okay? Those cavities, here we see an example. There's the blue X-ray emitting iron that's surrounded by a ring of the sulfur and oxygen. Okay? And why is it a ring? Well, it's actually cavities. We see the main shell as a shocked ring because as the forward shock went out, that forward shock, the original blast wave, as it encounters material, there's a reverse shock that develops and propagates backward with respect to the forward shock. And let me be coordinated here for a second. So it goes like this, okay? People think, oh, it's going backwards. Well, actually, it goes like this, and it slows, okay? But then at one point, it can actually, in our frame of sky, go backwards, but it originally goes like this in Lagrangian, and then slower ejecta end up catching up to it, okay? That's what we see in the optical, and that's why we have only these rings. If you have a cavity, think of a bubble solution, okay, a bunch of bubbles together. If we take a spherical cross-section of that, those bubbles turn into rings. Oh, and then the cool thing is, now we're getting at a stage where we aren't limited at core collapse models seconds after the core collapse, but they can be evolved into hundreds of years afterwards to directly compare with our observations. Okay? This is work by Salvatore Orlando. And it's not all Cas A. I know Cas A doesn't represent all supernova explosions, okay? Though sometimes I fool people into thinking that. Here's another iconic supernova remnant, the Crab Nebula. Okay? Older, descended from a lower mass star with a hydrogen envelope. Okay? And one of the other distinctive things about this, it produced a strong pulsar with a pulsar wind nebula that has accelerated the material. So contrast that with Cas A, which had a, let's say, 20 solar mass progenitor star where the hydrogen envelope was largely stripped. Okay? This is a lower mass with a large hydrogen envelope and a pulsar wind nebula that's contributed to the overall expansion. Now, I'm sorry, Bill, I don't have time to go over your paper, but I didn't want to flash that up to be a gracious guest. I'll encourage you to look at the paper. Maybe we can talk it about Astro Cafe. But I just wanted to, Astro Coffee, but I just wanted to show the incredible work by Thomas Martin in creating a three-dimensional reconstruction of the crab. Okay. Now, if you look at a 2D image, you see that it's different from, you see the crab is different from Cas A, but you can see in 3D how different it is. Okay. And whereas in Cas A, there was, you know, a half a dozen of these cavities, in the crab, there was so many more, because the formation is a little bit different. This is largely driven by Rayleigh-Taylor instabilities. Driven by interaction with the environment, but also the pulsar wind nebula pushing in from behind. Okay? So the hope is to use these morphologies, and again, I'm trying to project everything in a Mercator projection, to get a sense of how the distribution of material can reflect the progenitor system and its explosion dynamics. Okay. Oh, and by the way, if you ever visit Purdue, I'd love to take you into the Envision Center. We've got this augmented reality set up where I can actually take you into the crab or Cas A and explore things like you're there. Okay. All right. Now let's talk what JWST brings to the table. Okay. So I was fortunate to lead a team in cycle 1. We were awarded time for a variety of scientific objectives. I'm going to highlight in particular number 1 here, mapping unshocked ejecta that can be directly compared to current supernova simulations. That main shell, that's reverse shock material, but of course there's ejecta interior to that has not yet encountered the reverse shock. And that's gas that's closest to the explosion, which should be able to tell us a lot about the explosion dynamics. That is cool gas. The main shell is X-ray UV bright shining photons inside, and the gas inside is around 100 K. So we need to observe that in the infrared. Perfect for what James Webb is for. Other things we did that I won't have time to discuss here, well, actually that's in the progress of looking at dust properties and understanding density contrasts, and we are able to look for the neutron star. We didn't detect it, but we're able to put upper limits on. I mean, the question is, why is the pulsar in the crab so strong with a magnetic field, but in Cas A it seems magnetically inert? Okay? So one of the scenarios was fallback accretion at the time of core collapse that buried the magnetic field, and maybe there was a relic disk around it. We didn't observe it, but we were able to put constraints on that scenario. Okay, so just because I'm amongst people that will appreciate this, of course we were excited for the launch. We had our own launch party that morning, that Christmas morning in 2021. People were excited, okay? And I know it's not fair to do, but people do it anyway, compared to what Spitzer had done previously to what James Webb could achieve. So this is Spitzer at 24 microns of Cas A, a side portion of it, and now I'm going to enlarge it, okay? And it's always, you know, I never get tired of this. Sure, I could see something here in the Spitzer data, but it's so low signal and poorly resolved, it's fluff, right? You don't give it any significance. But when you have the resolution and that sensitivity, whole new stories begin and whole new opportunities for science open up. Okay? Here is an already beautiful image of Cas-A made by HST. I showed you this earlier. And now let me directly contrast what it looks like with James Webb. Okay? And notice the difference both on the outside and inside of the main shell. So again, this is the reverse shocked material. So Webb, because it's in the infrared, it's sensitive to the dust that has been shocked in the circumstellar material. So that's what we see in the red surrounding here. And then we also see that unshocked ejecta interior. I'm going to talk more. This really screamed out, and that was a real red herring for a while. I'll talk about that moving forward, okay?
Green herring.
Green herring, yes, very good. So yeah, it's the reverse shock. This is the dusty CSM material. This came to be determined as the green monster. Why green? Well, when we did composite images, integrating all the filters, it seemed to be strongest at the ones in the middle between the extremes, which popped out in the green the most. Okay, and then adjacent to it is this unshocked ejecta, and I'll show that in detail in just a moment. Okay? And then now the near cam image, notice the difference. Okay? We're going to shorter wavelengths, hotter temperatures. We no longer see that interior material. We see this campy smoke fire like light emission, that synchrotron emission from the forward shock wave, and that in projection with these cells. Okay? There's that synchrotron radiation. And then a serendipitous discovery was a light echo there in the corner. Okay, now there's people here that are working on light echoes around Cas-A. For those unfamiliar, this is light from the original supernova going in all directions and encountering ISM, unrelated. And for it to be so close, I mean, if this is Cas-A, it's like way back here, very close angle. And then it's come towards us in that time. I'm not going to have a whole lot of time to go into detail, but we'll see. Okay, and I will say we were very fortunate. People were excited about cycle 1 results, and because the Cas-A images, you know, could be appreciated by kind of somebody who didn't know much about it. We got a lot of airtime. There I am on 60 Minutes. This was a subsequent press release. My gosh, they did a beautiful job on this. Thank you, Alyssa. And it got picked up by the White House. Jill Biden wanted to do an advent calendar, and she chose this image for something representative of space in cosmic exploration. So following that, got picked up in the New York Times. I'm sitting down to watch the evening news, and Nora O'Donnell is announcing it. The next morning, Savannah Guthrie is talking about it. I watched the National Space Council meeting, and you can see, well, there's Kamala Harris there, but there's Cas-A. Now, I must say, I know there's no right side up in space, but it really pains me when I see a loved one hung upside down like that. It's just like, I can't handle it. It's not supposed to be like that. And then, yeah, with billions of potential views. And then, hey, I'm just going to mention it because the timing is something else. It was picked up as Astronomy Picture of the Day a couple weeks ago. The same day I'm in New York at the American Museum of Natural History. You know, they got dinosaurs and they got these exhibits. And there it is, an exhibit. Right? Like a proud father, I had to take a picture of it, okay? It showed up in an IMAX film. Here's a beautiful composite Webb with Chandra and Spitzer, and that showed up on the cover of National Geographic. And then one more thing, there was a whole CNN documentary that followed early on in our analysis. I mean, they followed us for over a year as we went through it. They came to my home. They went to an actual group meeting. And by the way, I don't know if you ever get a chance to do this, but I invited my class and just people, friends and family to partake in our viewing of the NIRCam data for the first time. And, I didn't have them sign non-disclosure agreements, but just say, don't tell anybody about it and stuff. So they loved it afterward. They loved to see scientists getting excited about things for the first time. And of course, some of the interview was recorded right here in this auditorium. And there's Ori Fox, and I've made a great meme with Ori from his showing there. Yeah. We're all astronomers, that's right. All right, there's been a tremendous scientific output from these data. This is the first batch of 6 papers. There's another 6 papers that are underway, should be coming out in the next year. This is my favorite figure from the survey paper that reports the overview and some of the major findings. First question, what is the green monster? Remember I said I wanted to identify ejecta, unshocked ejecta, closest to the explosion center. I thought, oh my gosh, it's so bright and obvious. Okay? But fairly early on in our analysis, it became clear that this was not the interior ejecta. It was dust-like and had properties that were much more like the circumstellar environment around it. Okay? And that analysis came from various ways. I mean, yeah, I will zoom in here. What blew me away is just the substructure. Do you see how round these holes are? There are a few phenomena in the universe that can make things that are so round. Okay? So one of the ideas was that maybe there were nickel fragments that had pierced in the interior and caused, that nickel bubble expansion that I talked on large scales. Maybe it was shrapnel in there. Anyway, that's not the case. But the roundness of those holes were really something else. So using X-ray analysis, where they compared the abundances of the green monster region to circumstellar materials seen elsewhere, and then using the MRS spectroscopy and near-spec spectroscopy that all pointed to abundances most consistent with the CSM. So the takeaway point is it seems like the green monster, if I'm Cas A, the green monster would be a dense sheet of circumstellar material that's lying between us and the interior. Okay? That opens up a lot of questions like, well, first of all, why is it green? We still haven't quite got it because the other material was red, if you remember. Okay? But like, what causes that pockmarked feature? Okay? And why is the material distributed like this? What special phase of the stellar progenitor contributed to this mass loss episode? Okay. Here I'm showing effort by Salvatore Orlando to model what's going on. In essence, there's 2 ideas. One is that we have small fragments of ejecta, the shrapnel, that has pierced through and formed bow shocks that open up the material. Another depicted here is that we're at the boundary of the forward shock, and Rayleigh-Taylor instabilities have these fingers that push out ahead and cause the black holes to form, at least as we would observe them, holes of where we have the forward shock penetrating outward. A lot of exciting things to think about here. We often model as supernova with spherical energetic output, interacting into a smooth wind. But here we have a very different scenario where the mass loss is very clumpy and concentrated in regions, and that disrupts the forward shock wave and it becomes much more corrugated, changing the progression. Okay. All right, this is the next series of slides I'm most excited about. I think it's one of the biggest takeaways and discoveries from our program. This is the F2550W. You should be familiar. This is the longest band pass that we have with MIRI. And from this, I wanted to be able to extract the unshocked ejecta. It's like a Rorschach test, isn't it? It's like, what's going on there? And I just told you that the green monster is kind of photobombing our ability to see the interior because it's in front. Okay? And that's largely this stuff that we see here. And just to be clear, I've really burned in the image here, showing wherever there is emission possible. So I'm going to now invert the color map. Okay, so what was black is now white. And then doing a little bit of work in subtracting the 2100 W filter and adjusting for where we think that there is dust. So there's some component with dust and some component with synchrotron. So doing the proper adjustments in the level of subtraction, we come up with this. So this is beautiful to me. I hope I can convey the beauty to you. Okay, so this is all the reverse shocked material. We're unable to kind of peer beyond this, okay? But the green monster, because it's largely dominated by dust emission, which is fairly well modeled, okay? We're able to subtract that out and leave behind the unshocked ejecta. And it makes me speechless every time. So this is what the gas closest to the explosion looks like, and it's this web-like network of filaments. Okay, and for those who are familiar with the remnant, some things start popping up. So, for instance, in this area, we know that there's a strong outflow of X-ray bright emission. And here we can see some filaments pointing in that direction. In this direction, remember I said that there's these this northeast jet-like fast ejecta moving almost 15,000 kilometers per second. Right down the middle of the barrel is this filament pointing out in that direction. Okay. Then there's other things I don't have an explanation for. I don't know what this is, and I don't know why it bridges out in that branch there. Okay. We can go further. This is just an image. Remember I talked about 3D reconstruction. So the program also came with 4 pointings for MRS and near spec. And one was here. This was our deep drilling. Another one was here, selected to go over the green monster, but it also samples the inner ejecta at that point. And then the other points are for bright main shell ejecta, which aren't relevant for this discussion. But now, so this is new work by Danielle Dickinson in place. Here you can see the MRS detector, and she's scanning through. So you got to think, we've got this tiny footprint on all the remnant, and you see the variety of emission and filaments, and we're just barely getting the right resolution with the 2550 filter. Here we can resolve it down to less than an arc second. Okay? We have this tremendous, think of the scale, this tremendous explosion that's parsecs in size, okay? And we have these filaments that are 0.01 parsecs in scale. Okay? So our aim is to compare this to simulations to see, I mean, I can tell you already, we started doing that, and the simulations aren't able to reproduce this level of fine scale structure, so it's really pushing them to go back and increase resolution and understand where this level of structure can originate from. Okay, I'm looking at the time, so I'm going to move ahead. Here's a multi-wavelength image. Here is that simulation that I was talking about. So in red is nickel, in blue is the oxygen. So if the blue has been shaped by the nickel early on in the explosion, forming this web-like network, he can recreate it. This is Salvatore Orlando again, to some extent, but he can't, it's mostly a cage of emission as opposed to emission going all the way through, as that scan showed you. This, he says, means that there must be some additional contribution beyond neutrino heating and nickel bubbles that was used to create this. Again, with the notion of shell mergers. Okay? Shell mergers are a way to really disrupt that progenitor interior and kick up the turbulence to mix much more material back into the inside. Okay. With the little bit of time that I have remaining, I just want to highlight the work that people are doing here in light echoes. So here is Cassay multiple epochs with Spitzer. Okay. Look at this awesome stuff. So these are thermal echoes. This is, again, light from the original supernova heating nearby ISM, and it, through multiple epochs, we see it scanning through the ISM. Okay. I mentioned that in our observation, we just happened to catch that light echo in the corner. I want to emphasize how lucky that was. Okay? Rob Feason has a Cycle 4 program to return to Cassay with near-cam observations, and those were recently obtained. And I'm blinking back and forth between ours originally and the new ones. Look, first of all, it's a transient thing, because we know it's a light echo, right? And the detector configuration rotated ever so subtly, and we miss it altogether, okay? So we really, really got lucky on this, okay? I could spend, again, whole lectures understanding all the other weird light echo stuff. You can see stuff coming and going rapidly here and there. Yeah, but this is what it looks like zoomed in, okay? Somebody said it looks like a xenomorph from Aliens. Another person said it looks like a Brussels sprout. But anyway, the level of structure, when we first opened up the data in that meeting that I mentioned, we thought, is there something wrong with the detector? Is there a scattered light? I mean, it was a really bizarre thing. So, many questions come up about how this structure can be introduced. Is the dust not mixed uniformly into the ISM gas, or is the dust also structured this way? Are magnetic fields involved? Is this a structure typical of large ISM clouds? Okay. Great science. All right, I can continue going. Yeah, in the interest of time, I'm just going to continue moving forward. What has James Webb done for other supernova remnants? So returning to the Crab Nebula, I point you at the incredible paper that Thea Tamim put out. I mean, she's basically covered the crab in so many ways. She's done a very thorough job with the analysis. Again, what's remarkable with the crab is that we have a pulsar wind that has moved so much of the ejecta. And the question is, well, what's the explosion scenario? Okay? How do we have such a low energy event? If you count up all the mass and how fast it's moving, you get a kinetic energy of 10 to the 50, maybe even less. Okay? Standard supernovae are supposed to be 10 to the 51 ergs. So what was the origin? A lot of people thought it was electron capture supernova, different progenitor scenario. Okay? She was able to test that with James Webb, in large part because we win in resolution. So there's the Spitzer 24 micron observations. Now we're going to enlarge. Okay? Notice the dramatic increase. So we're finally at a stage where we're resolving the filaments at a scale of the filaments as opposed to blurring it all together. And the crab is this careful combination of shocks and synchrotron. And so how you model abundances has to be taken into very careful account, the energy source and the temperature and density effects, which can change as a function as you move along the filament. Okay? Hence why you need the resolution. Okay? So they performed spectroscopy, sampling the nickel to iron abundance ratios, and they found ratios that were consistent with a low energy core collapse. So when the original claim of electron capture supernova was done in a time when we didn't really know of low energy core collapse simulations, but nowadays we have a variety of explosions at the very lowest end of massive stars that can produce low energy explosions, and those nucleosynthesis yields are consistent with what they measure from the Webb data. Okay. Although I have to be clear, and Tay always reminds me to say so, electron capture scenario cannot be ruled out with the data. Okay? Cannot be ruled. An additional contribution to why they favor, or at least, why the low mass scenario is favored is that electron capture doesn't really produce a fast-moving pulsar afterwards. In the case of the crab, that pulsar is moving around 150 kilometers per second, which seems to be not easily made in electron capture scenario. Okay. And then back to 87A. Revisit, old friend revisited with new technology. I'm sure you've heard about this discovery. So that surviving neutron star. I mean, it seemed like every year there was another claim to find the surviving neutron star in 87A because they wanted it every year. I think this is the claim that's going to stick. Okay? And let's be clear, it's not a direct detection, it's indirect in that when they scan through and look through for emission lines, let's say in this case argon, they see this central source pop out only at certain emission lines. So it seems to be the scenario that you have the neutron star heating material around it, or some confined pulsar wind nebula that's ionizing material around it. Okay? But this opens up other possibilities. Actually, I've put the notion out there. We should be doing this for extragalactic supernovae, looking in these lines for supernovae that are decades old, and maybe the way to see that surviving pulsar wind nebula interacting with the surrounding ejecta is through this similar analysis. Okay, and moving forward of other remnants that we can do. Okay. Here's a listing of all the remnants. In cycle 3 was 0540 by Josephine Larson. And then cycle 4, finally, and thank you whoever's on the TAC for cycle 4, we got type 1A remnants approved. Okay? That includes Kepler's supernova remnant and PA30. And I'm just going to advertise now, there's a lot more opportunity for other remnants to be observed in the same way, okay? Using the techniques that I've described here. But since I'm amongst friends, okay, I'm going to show something that I'm going to ask that the video be cut for people watching this remotely, and you'll feel special because you're only going to get to see it here. So we have a cycle 4 program on Kepler. Kepler's a bizarre object. Okay, it's often mistaken for core collapse because it has this asymmetry to it. It's a thermonuclear explosion of a white dwarf that's been interacting with nitrogen-enriched circumstellar environment. Seems to be the classic case of, white dwarf accretes material from a donor star. Okay, but very deep observations have not been able to find that donor star. So how do I have all this circumstellar material, but no obvious donor star? 2 white dwarfs should not produce this environment. So we got the time to observe. This is Spitzer at 24 microns. And then we're going to enlarge around. Are we killing the video now? We got thumbs up. Okay, very good. And I don't really care, but I do. So this is with Spitzer, pixels, stuff's happening. Okay, so once again, we can actually really get a sense of this hole, this rupture in this area. You see that the filaments are finally being able to be resolved and to compare with other observations like Chandra and HST at the arc-second level. And then the thing that that's not such a wow. This is the wow to me. So this is what we're looking at with James Webb right now in the I think this is a 2100 filter. Okay, so I'm just going to scoot ahead now. So I hope I've conveyed to you that, I've taken this bold claim, supernovae sit at the crossroads of astrophysics. They have so much importance in a variety of astrophysical settings, and yet there are critical questions about their origins in explosion physics. And these uncertainties ripple outward, affecting the fields that use supernovae as inputs. Okay? So we're now in an era where JWST provides resolution spectrally and spatially to dissect supernova explosions in detail at infrared wavelengths that provide a lot of important tools of analysis. Okay? I hope to demonstrate here that observations of CAS A have been able to show the unshocked interior ejecta and the surrounding circumstellar medium that encodes information about what the star was doing leading up to core collapse. And I'm advocating that additional observations of core collapse and 1A remnants are needed. And with that, thank you very much.
Okay, thank you, Dan. That's great. Let's see if there's any questions in-house here. We've got Jason down here.
Hi, beautiful talk, beautiful data. Thank you very much for that. People who study galactic chemical evolution at much larger scales than individual remnants are relying on the assumption that a yield of a supernova, carbon, nickel, iron, all the elements we're used to studying, is more or less a deterministic outcome of that star's initial mass, right? Now, that's probably never been true, but this idea you have that the turbulence in the star before it explodes can affect the shape of the remnant suggests that maybe the yields are very stochastic, considering and not therefore a strict function of the initial mass. Is that a real issue?
So if there were people who make these models, nucleosynthesis yields here, I know the majority would take not offense, but would not hold that viewpoint that it would be stochastic. So let's say the bulk output is somewhat rigorous, but my counter to that is I think additional work needs to be done, and certainly we need to understand the mechanism that's providing this additional asymmetry, because depending on the mechanism, that certainly can influence the nucleosynthesis yields. Okay? And it'll, of course, certain elements will be more affected by it than others.
Really fantastic talk. So when you were showing this 3D view of CAS A, it looked like the central neutron star got a pretty decent natal kick, right? It was sort of asymmetric from the center of the bubble. Does the position of that central remnant hold together with the sort of asymmetry that you see in the ejecta?
So let me quickly refer to the animation. The answer is yes. So, right. Let's do this one. Great. Okay, so I'm going to pause it. Nope, I'm not pausing it right here. So, the motion of the neutron star is in this direction. Do you see that? Okay. And then opposite, do you see this and that? And I'm going to rotate it around. Opposite is this very large, actually we can even go further. Right there, okay, is the largest ring where there's a deposit of X-ray emitting iron. So momentum seems to be conserved, yes.
Thanks.
Yeah, thanks for this beautiful and interesting talk. Follow-up sort of related to Jason's question, even though I guess he had to leave. So the other thing, galaxy formation models use these sort of ideas for is how energy or momentum gets transferred into the bigger picture. At detail level, obviously they're not like nice little spherical energy injections or momentum injections, but at some scale that's kind of true on some level. Basically I'm asking you, is your entire field one resolution element and that's still okay? Or would you argue that this is actually really important even at the much larger scales?
That's why I'm at a place like this to have those conversations. Honestly, I don't know if anyone's done the work to say, okay, if this level of stochasticity, turbulence is introduced in the environment and we run the simulation out, what influence does it have on the final outcome? I don't know, right? I mean, certainly at the level, even the ISM, you see the light echoes, right? So how does that affect the influence of shocks as it's propagating? So it's a sense of scale. I'm most immediately wondering about how this influences our interpretation of extragalactic supernovae, where we see interaction with circumstellar environments, so that's on a smaller scale, given a sense that we know that it's clumpy, so that will drive which emission lines are observed, and so people assume spherical symmetry, but if it's clumped and localized, that's different than a uniformly distributed thing.
Maybe just before we come back in the room, let me just ask if anybody online has a question, and if you do, please unmute and go ahead and ask. I'll give a few seconds. And if not, we'll come back in the room here. Hearing none. Okay, Kevin.
So you showed the pre-explosion light curve of 2009 IP.
Yes.
What's known about the pre-explosion behavior of 1987A?
Oh, very good. To my knowledge, nothing. I know that there were some archival observations, but I don't think that anything was obvious in that scenario.
There's no reason, I mean, we might have missed it, but there's no reason to think that that one experienced the same brightening that...
That's right. But yeah, if anybody's online and is more familiar with the literature, but nothing jumps out into my memory that showed that, certainly not at the level of what I showed for 2009 IP. That's right.
Ravi, who would have thought supernova remnants are so exciting?
Saying you.
The question I had was, so in the green monster, there's little circular things.
Yes.
The two explanations you gave were both like things moving forward.
Yes.
Is the other way possible, where you have pre-existing structure in the circumstellar medium and a flat shock going past, and it's the pre-existing clumps that are creating these? So can you tell the directionality of those based on the images?
Well, we can talk about that. So you're saying, sorry, inhomogeneities in the sheet?
No, inhomogeneities in the pre-shock medium and the circumstellar medium, you have little clumps because those have been, they're clumpy. And
okay, so you're starting from a prior where the environment is clumpy, but the mass loss is smoothish or something?
Smoothish, and you get the holes where the clumps are.
I haven't heard that scenario. I would wonder if you could get the density contrast to be significant enough to show that. That's interesting, though.
One more here? Yeah.
So I see a lot of similarities between what's happening with supernova remnants and what's happening on galactic scales with like active galactic nuclei. So is there any sort of bridge that has been thought of or talked about on looking at how these kinematics and these outflows and shocks can be interpreted on a galactic scale, and how they could like scale them up?
Wait, you got to help me with the connection between remnants and AGN.
Right, because you're seeing a lot of these outflows and these shocks. We're seeing a lot more signatures of mechanical feedback happening with these outflows, depending on the coupling strength of the host to the central engine. So there seems to be a lot of overlap potentially between what you're learning on the nearby scale versus what you could then ramp up and apply to galactic scale feedback processes.
Okay, I'd be delighted to talk further about that. I haven't even thought about that, yeah.
Okay, well, we'll close with one more question. I was just going to say, we're sort of, in supernova remnants, we have a blessing and a curse. They are multi-wavelength, so you've got all this different information coming from different sources out there, but getting things on roughly the same resolution scale has been a problem, right, until now. So to have the Webb come in now with comparable resolution to Chandra and to Hubble and so forth is really allowing us to look at the different pieces in a different way than we've been able to up until this point, right?
100%.
Yeah.
Yep.
Yeah.
That's why the comparison with Spitzer is worthwhile here, just to show what we had previously only accessible in the infrared. We needed Webb. Yeah.
So the part of the problem there, of course, is that you're seeing different things in those different wavelengths, and how do you put all that information together with the models and everything else? It's pretty complicated. But one last question?
Just another quick one. You may have said this already, and I apologize if you did. So the rotation axis of the remnant. Is there anything important there with the structure
of Cassay's neutron star?
Or any of these things? Yeah, exactly.
Okay, so we don't know anything about that neutron star. Okay, we don't see any pulsations. We have no sense of that. I mean, in the crab, though, certainly there's a symmetry. We can see its disk and the outflows, and we see, morphology reflecting that axis.
Got it.
Yeah.
Okay, well, listen, we're going out to dinner tonight with Danny. I do have a couple of slots left for dinner. If anyone is interested, please let me know. After the talk here or at SDS, we'll be going in there in a couple of minutes. And let's thank Danny again for a great.
Great.
That's less beautiful.